Um, I sent you guys the practice midterm today in an email, and even getting you guys that email was a challenge because the other site, MySlick, where I can get all your emails, was just like crashing over and over. You guys felt that too. I imagine it had something to do with Canvas not working, so everybody was going to MySlick, and we were probably just crashing the system.
I'm not gonna lie, I got a notification that one of my things was graded, and I clicked on it. It's like we can't find the course, and I was like, I've been kicked out of the course.
Oh no. Part B, which I believe I gave you guys some heads up about building a structure. We even practiced it a couple of times in class. Part B doesn't resemble any of the graded part of your practice midterm, and in a similar way, it won't make up any graded part of your actual midterm. I gave you guys an hour for Part B, yeah, to solve that structure. I'm giving you 90 minutes for the exam. So I'm not anticipating that you'll have the same amount of bandwidth to solve a structure like that. Although you will see that there is a bonus question worth 2 points where you're doing kind of a similar problem. You're given a chemical formula, you're given an IR and an NMR, and you're asked to solve. So if you felt good on Part B, then you might get some points here. If all you felt good on was IR, then you can get some points for IR. Notice that here I'm actually asking half of the bonus points just come from annotating the IR. I want to see how well you can interpret that. But in the same way, the ability to interpret NMR is what gives you that chemical structure. I wanted to give you that feedback on Part B to say, here's what you did right in your IR, here's what you didn't, here's what you did right in your structure, here's what you didn't. Here's some feedback on your molecular ion. Here's some feedback on your, how was that question phrased? Did the NMR speak towards the functional groups at all, right? I want to give you some feedback on that, and I wasn't able to give you that feedback today. So if you have questions on those same topics, we can go over them. Otherwise, you'll get feedback on those tomorrow. Maybe tonight. We'll see how much energy I have tonight. But otherwise, midterm and the final, cumulative. So you're going to see things from Unit 1, Unit 2, Unit 3. So let's build a list and let's go through those concepts. They can be broad concepts or they can be specific concepts, specific questions that you've seen on active, on old material, on the practice midterm. I'm ready. Elliot.
Resonance form stability. There's a question on the bit about ranking them. I don't remember.
Sure. We'll look at that for sure. That's a big one, by the way, so that's good.
I'd like to go over the mass spec again.
Okay. Anything in particular about mass spec?
Mostly just the patterns and how to interpret them.
Okay. So I'm going to put the 3 most important things about mass spec, which is the base peak,
I guess
the molecular ion, and the daughter ion.
we'll always have the chemical formula when we get a question like that, right?
Yes or no. I mean, sometimes you're given structures.
The structure's fine. There's a couple questions on active that doesn't give you the chemical formula, and
yeah.
that's what I was having a hard time with.
Yeah. You know what? We can look at those specific ones on active. If maybe you want to pull them up, and we can look at them together. We can come back to this.
Yeah.
Yeah. Will.
Two things. I would love to go over some of like the specific nuance, like comparing like what a Lewis acid base and a Bronson-Myrick acid base is. And I would love to do like not like a super in-depth, like a quick refresher on how you actually.
Okay. Well, while we're on that, what functional groups will you be tested on with nomenclature on this exam? So you will be asked to name and or draw alkane and alkyl halide functional groups based on their nomenclature. Although you might notice the midterm, the practice midterm, has a multiple choice question that is on nomenclature more at large. So you get this structure, and it says, what is the root for the parent chain of the starting material? It actually gives you the whole name, and then it just breaks it up. So this is asking you, do you understand the terminology of IUPAC? And I think it is fair for me to give you guys a multiple choice question on nomenclature. It's kind of a softball. Yeah, is that, sports is not a good analogy for me. It's kind of an easy question, in my opinion. Even if it's not necessarily on alkane or alkyl halide functionality, it would be on a broader concept within IUPAC nomenclature that should be relatively easy to interpret and understand. So we'll go over IUPAC nomenclature. We're going to look predominantly at alkane and alkyl halide, though. Yeah?
Yeah, the basics.
Okay.
Just basic breakdown of how you do it.
Aiden?
Well, you got that pulled up. Are racemic mixtures only when there's an even amount of functional groups coming out? Because, like, I know that it's a diastereomer, but, like, it was tripping me up for a minute because two of the groups changed, like, evenly almost in my head. So I was thinking, oh, maybe it's racemic because, you know what I mean?
Yeah.
It only works if there, in that example, if there was, like, another bromine, for example.
Okay, so anybody want to help Aiden out? The definition of racemic mixture. Aiden mentioned 50-50. Good. They have to have a specific relationship. In fact, these two names are almost the same. If an enantiomeric mixture is 50-50, then it's called a racemic mixture. But you can have enantiomeric mixtures that are 25-75, in which case you've got a 50% enantiomeric excess of one over the other. Or 90-10, and you've got an 80% enantiomeric excess. Or 95-5, 90% enantiomeric excess. Those are enantiomeric mixtures. All racemic mixtures are enantiomeric mixtures, but it's specifically at a 50-50 ratio. Diastereomeric mixtures, whether it's 95-5, 90-10, 50-50, are always called diastereomeric because diastereomers do not necessarily have equal and opposite rotations of plane polarized light. And that's where the definitions for these come from.
Gotcha. Okay, that makes sense.
The relationship between these?
Diastereomers.
Right. And you mentioned it's like they're almost the same, but they're just slightly different.
Yeah, I overthink it.
That's true. In fact, what you're catching on is that there are two things that relate about these compounds. At least one stereocenter stays the same, and at least one stereocenter changes configuration, and that's true for two of them. That's our definition of diastereomer. These two things are true about the two compounds. Good question. Indigo.
Can you go over the priority thing, decide if it's R or S?
R and S, definitely. Anybody else? We can come back to add more on if we need to. All right, let's look at resonance and ranking resonance. Can we get a definition for resonance before we really dive into this problem? sometimes. Yeah. So resonance is the movement or delocalization. Two terms that can both be used interchangeably but have very different feelings. The movement or the delocalization of pi electrons. So of course all pi bonds can be involved in resonance, but also lone pairs can be involved in resonance sometimes as well. In fact, we use resonance as a ranking in acid-base problems. We say a conjugate base or a conjugate acid that has more resonance is more stable, which makes it a more reactive base or a more reactive acid that it is the conjugate of. Okay, so here is an acetate group. That's the conjugate base of a carboxylic acid. We said carboxylic acids are more acidic than alcohols, a similar OH group, because they have this resonance. Now it looks like the pi bond has delocalized. It looks like the pi bond has moved, when in reality, it's also the lone pair of electrons on O minus. A lone pair has been shared by one oxygen, and a lone pair has been taken back by the other oxygen. A pi bond has formed by the lone pair being shared, and the pi bond broken has turned into a lone pair. So pi electrons don't always have to be pi bonds. They can also be lone pairs, but you'll notice that those lone pairs then create pi bonds, so we can call them pi electrons. Which of these resonance forms is a more major contributor? Natalie?
Actually, never mind. I don't know.
Why don't you know?
I was thinking like orbitals, but I'm not really sure where I was going to go with that.
Okay, actually that's okay. I think you're thinking of Cario with
Yeah.
acid base again, and thinking one of those looks like an sp3 oxygen, and the other looks like an sp2 oxygen. And that's something we use to rank acidity. Although, if these two resonance forms exist, the atom that is sp3, or the atom that looks sp3 hybridized, being sp2 hybridized in the other form, is it really sp3 hybridized? Ever? Because what's true of these two structures? Do they exist at different times? Do they exist at all? They don't exist at all, and they don't exist at different times. They exist at the same time, and it's actually just two ways of drawing something that exists. So if it looks sp3 here, but it looks sp2 here, it must actually be sp2 all along. It can't have a different hybridization here than it does here, because it doesn't exist like that at all anyways. Anybody else? Which of these is a major contributor? A more major contributor? If you feel tricked, just say that. They're equal contributors. Because there's no change in charge, there's no change in octets, and there's no change in which atom holds the charge. And those are our three rules. First, minimize charge. 2, maximize octets. I'm going to have a sub-point here. And 3, place charge appropriate, or appropriate charge placement. I think when I introduced this in our first unit, I talked about that maximize octets and how there's actually one atom in particular that you can look to try and maximize its octets. Otherwise, pretty much every single atom is going to have maximized octets. Do you guys remember what atom that was? Yeah. If you're going to maximize octets, you're pretty much trying to maximize bonds to carbon. So yeah, you know, I think I found a downside to that though, which is carbon can have an octet and still only 3 bonds. That's if carbon has a lone pair to itself. So it's increasing the bonds to carbon instead of having a carbocation, a carbon with a positive charge. It's a little hard to say, but most of the times you're trying to maximize an octet, you're trying to make sure carbon doesn't have a positive charge. That's what you're trying to do. Okay, so because of those 3 rules, these 2 resonance forms are exactly equal to each other. Let's look at some other forms then. Okay. Yeah. Good point. First, let's look at this one that I've drawn up to the right. You can see it's an aromatic ring with O- coming off of it. And then it's what looks like a ketone with a negative charge on the carbon next to it. Can you rank those 2 forms? Aiden?
The one on the left is the, I guess what's the term, better contributor?
More major contributor?
More major.
More stable?
More stable, yeah.
And which of these 3 rules have you used to identify that?
Maximizing, well, no, appropriate charge placement.
Good. Charges don't change between the 2 forms. All of the atoms have octets. If you're not convinced on that, remember that table that I made you build during our second week of classes that I want to have you feel like your ABCs. I want you to recognize bonding patterns and charges on these atoms. That negative charge on carbon means it has a lone pair. Not to mention, bond line structure tells us there's a hydrogen bonded there as well. So that's 3 bonds to the carbon plus a lone pair, that's 8 electrons. So everything has octets in that structure. Then it's just about deciding, is it better for me to place a negative charge on carbon or a negative charge on oxygen? How do you decide where a negative charge is better held? Electronegativity, exactly. All right. I want to look at this one before we look at what we've got on the screen there. Here is an isopropyl group bonded to an amine off the central carbon. And then actually what looks like a protonated imine, CN double bond, positive charge on the nitrogen. Anybody else? What's our more major contributor in this resonance situation? The one on the left? You want to give which of these 3 reasons? Oh, I don't think so. It looks like a positive on the left and a positive on the right. So same charges. Huh?
The more stable one would be the one on the right, just because the charge isn't
Okay, so we said earlier, negative on the oxygen is stabilized because oxygen is more electronegative. Yeah, let me pull electrons towards me. But when it's a positive charge, who wants to pull electrons towards them? Nitrogen or carbon? Remember, what we're looking at here is a lone pair on nitrogen that's being used to create a pi bond. Who wants electrons more, carbon or nitrogen? Didn't you just say nitrogen is more electronegative?
I didn't see the positive. I can't see.
Okay, don't worry. Deep breath. Which atom pulls electrons more strongly, nitrogen or carbon? What's another way of asking what I'm saying? Which atom is more electronegative, carbon or nitrogen? Nitrogen is more electronegative. Nitrogen pulls on electrons more strongly. Nitrogen should be the atom that's holding on to the electrons. That'd be the structure on the left. So appropriate charge placement, structure on the left. Carbon takes a positive charge better than nitrogen does. Nitrogen takes a positive charge better than oxygen does. But we skipped over rule number 2. We got to maximize octets. That means we're basically trying to maximize bonds to carbon. So which structure has more bonds to carbon? Structure on the right. That means the structure on the left doesn't have maximized octets. Can you guys verify that for me? How would you say it? How would you verify that the structure on the left doesn't have maximized octets? And no lone pairs. The carbon in the center has 3 bonds, no lone pairs, that's not an octet. The carbon on the right has 4 bonds, an octet. So this structure, despite placing the charge inappropriately, has obeyed rule number 2, which means that's a more major resonance point. All right, and I'm actually I'll leave you guys to solve this one on your own. I'm sorry, by this one I mean I'll leave you to solve the midterm problem on your own. But let's go through this one together. My resonance arrow died. Okay, I've actually taken this structure, I've modified it a bit. It's still a 3-carbon chain, but now an amine and an alcohol are located on this end, primary carbon, and I've got an alkene. We call this allylic. These positions are allylic because they're adjacent. They're on a carbon adjacent to the alkene carbon. Then we can see oxygen must be sharing a lone pair, which creates a double bond. Then nitrogen shares a lone pair, which allows oxygen to take its electrons back. And to get to our final structure, we're seeing that the nitrogen takes electrons back, and the alkene pushes the pi electrons onto one of the 2 carbons. Why don't you guys work in your tables to rank these structures from lowest priority or lowest contribution, least stable, to most contributed, most stable. appearance too. Yeah, so it's on the carbon in the first structure, it's on the carbon in the second structure, despite that, the fact that electrons have flow out towards the carbon.
First of all, how the hell did that carbon get to
How many bonds to oxygen in that second structure? It has a full octet in the front. The oxygen has a full octet at the start, and it has a full octet in the second form. All it's done is shared electrons. It hasn't lost. Sorry, how many bonds to the O in the second structure? I see two carbons in the oxygen. And then there's one. So your bonding patterns, when you see three bonds to O, there should be a positive charge. Not significant. Another way to look at it. Carbon has a positive charge in the first thing, and now oxygen is helping to alleviate carbon's positive charge by giving some of its negative charge. So what effect will that have on oxygen? When one atom tries to help out with a charge, like that. Did you determine the least stable? So like this. Easy? Good. Yeah. Which one confuses you the most? The first, the second, the third?
2, 3.
The second and third.
Between, yeah.
All right. Let's go through these together. Which of these is the easiest to rank? The one with three charges. The one on the far right, the one that is the most stable. Least stable, right? Why is this the least stable? It maximizes charges. You literally can't have more charge in this structure. So that's the least stable form. The molecule doesn't look like this. So we're going to call that number 4. That's our lowest ranked. And then what? Was it easier to find the most stable, or was it easier to find the second to least stable, number 3? What do you think? It was easier to find the second to least. So there was concern about the most and the second most stable. What was number 3? What is the second least stable form? The far left. So if this is obeying rule number 1, this must be obeying rule number 2. Carbon has a positive charge. That means that it doesn't have an octet. I haven't maximized bonds to carbon, but here I actually have maximized bonds to carbon. So a positive charge on O, doesn't that lack octets? If oxygen had a full octet here, that was a magic trick. Has it lost electrons in this resonance form? No, it's done what? Shared electrons. It hasn't lost any, it's just placed them in a different spot. So oxygen has an octet, it still has an octet with a positive charge. Nitrogen has an octet, it still has an octet with a positive charge. That's the weird thing about carbon. That's why I say maximize octets, but really it means maximize bonds to carbon, but really it means don't have any carbocations, don't have a positive charge on carbon. Okay, so now we're between these two. What is the difference between these two structures? Charge placement. We already decided that a negative charge is held better by a more electronegative atom, and we discussed that a positive charge is held better by an electropositive atom, which is a funny word. The less electronegative atom. So, which atom is more electronegative, O or N? O is more electronegative. So does it do a better job holding a positive charge or a worse job? A worse job. So here is number 2, and our most stable form is when nitrogen takes on the positive charge. You know, my organic 2 students are going through this same thing. They do resonance, but they do it in application of chemical reactions, which is why we introduce it now so that you have a foundation, and you're going to see it in reactions later on. And they still have the same instinct as you. They say, give the charge to the more electronegative. You've got to think about the charge. The type of charge matters. Here's the way that I think about this. Which of these atoms is more willing to give its electrons to something? Nitrogen is. Nitrogen is very willing to give its electrons because it's less electronegative. Which of these atoms is greedier and takes electrons when it can? That's O. Oxygen will take electrons when it can. Okay, is that a good review of resonance? All right. I expect to see that question aced on the next exam. Okay, let's talk about mass spec. And I think we can. Do we need to see examples of mass spec? Maybe it'd be best if I had the exam pulled up for this one. Oh, yes, yes. Okay, so a good reminder. You will always be given a structure or a chemical formula,
Okay.
unlike active.
Okay, we don't.
Let's look at it, though. In case anybody hasn't solved it, we can at least try to reason it out together.
It's the very last one on the section.
Number 18, section 12. Oops. Okay, perfect. I'll pull it up. Thank you. Okay, so this is a little bit more challenging than what you will have to solve on the exam at all. One of the reasons it's challenging is because it doesn't give you a chemical formula. It doesn't give you, it does give you a molecular ion. Okay, there was a part of mass spec I didn't teach you. Maybe I should have because it's not that hard. But usually I'm giving you a structure and asking you about fragments from it rather than having you solve it. You can take a chemical formula like the molecular ion equals 68 mass per charge. That's a molecular mass. And you can take that molecular mass and divide it by 12. What is 12? That's carbon's mass. You're usually going to get some decimal, but what integer value can you get out of 68 divided by 12? You can get 5 and something. So that means you've probably got 5 carbons. And the other 8 mass units come from something else. This isn't a surefire way, because if you've got nitrogens or oxygens in there, those can throw off your carbon count sometimes too. But for this problem, this is more than likely C5, and the other 8 mass units could only come from hydrogen. So C5H8. By the way, quick degrees of unsaturation calculation. 10 minus 8 plus 2 divided by 2. 10 minus 8 is 2, plus 2 is 4, divided by 2 is 2. There's 2 degrees of unsaturation in this compound. That could be 2 pi bonds, 2 rings, 1 pi bond, 1 ring. Those are our options. And we'll see if there's any other information in the problem that helps us along. We're also given some information about IR. We've got a signal at 3300 and 2100 wave numbers. Correlation table tells us that can only be one thing. That's an sp-CH bond and a CC triple bond. How many degrees of unsaturation there? 2 degrees of unsaturation. and I've used up 2 of my 5 carbons. So I have 3 carbons left. There are 2 ways that this could look. I could either, oh, it's really ugly looking. I could either have this little isopropyl looking thing or an N-propyl looking thing. Those are my 2 options. I'm not sure if you guys have plugged it in. There's a good chance either of them would be accepted.
Well, it would be the bottom one because the remaining mass, there's like a major fragment and the remaining mass is
So there is only one correct answer. You've tried both.
I've done the bottom one.
The bottom one works, but the top one.
I'm not sure if the top one does work, but like the bottom one is specifically 29, I believe.
Let's try it then, shall we? Let's see if the top one works.
I didn't try it.
I'm worried this is. Oh, they're not going to give it to me. Okay. Sorry. Let's talk about why that mass fragment at mass 39 which, by the way, we could call this what? M minus 68 is our starting point. To get down to 29 means we've lost, I don't know. You're allowed to bring a calculator in case that helps you at all. I'm going to say it's something with a 9 in it. 29. The M minus 29 signal has this mass at 39 mass per charge. What weighs 29? Okay, well, here's actually how we get there. A mass of 29 is not a methyl, which is the mass of 15. But if I add a CH2 group, which weighs 14, that does weigh 29. And which of these 2 structures can fragment off a 2-carbon chain? Only this one, where I get CH3 and CH2 that can fragment off. Here, I can't get these 2 carbons to leave without also taking one of these 2 carbons with it. So it is the only fragment that works, the only answer that works. 2 structural isomers, only one that can give a fragment M minus 29. Challenging, mainly because you didn't know the chemical formula. Let's look at a similar type of problem, but on the exam, so that you can see what you'd have to solve on the exam. Here's a mass spec problem. It says, which fragment of 2,2-dimethyl-1-butanol forms the M minus 15 signal? So you could start here and say, I'm going to calculate the mass of 2,2-dimethyl-1-butanol. It'd be a waste of time, honestly. Because it's not even asking you which of these peaks is the M minus 15 signal. It's asking you which of these fragments is the M minus 15 signal. What weighs 15 that I could lob off a compound? CH3, a methyl group weighs 15. Have I lobbed off a methyl group here? No. In fact, what is this? Yep. This is M plus, the highest mass in the compound, which is 88. Okay, what about here? Have I lobbed off a methyl group? No, here I've actually only lobbed off my OH group. So this would be the M minus 17 signal. The M minus 17 signal is not always a very loud signal. Sometimes the M minus 18 is louder, but you can see here M minus 18 would be 70 and there's nothing forming that. Okay, what about these 2? Do these lob off a methyl group? Well, they do. They both do.
But only
this fragment does not produce a signal. This is not the M-15 signal. This goes into the waste during the signal that creates a 15 mass per charge from the fragment that produces a 15 mass per charge signal. This is just waste. This doesn't create a signal at all. This produces the M-15 signal. Trick question. Yeah? Okay, how about this? Is the M-15 signal the base peak in this spectrum? That was a really quick answer. Who had that? Can you tell me why you knew that so quick? You didn't even have to do any math. Okay, and you know that this is not the M-15 signal because of what? You did that quick?
I did that a while ago.
You'd been thinking about it, okay. 88 minus 15 leads me here, M-15. Anybody want to calculate that? What is the 57 mass per charge signal? M-31. Which is not methyl, not ethyl. You can look at your correlation table. I know it's not given to you on the exam because it's really not very helpful. It's also not a tert-butyl signal. I think the tert-butyl signal is more than 45 because you've got 15, 30, 45, and 12. I guess that makes it 57. 57. There you go. It suggests the presence of an M-57 signal as well, and that would have a charge of 31 mass per charge units. And that would be what's left over, which is this carbon, this carbon and the OH would be left over. And actually, we talked about alpha cleavage here. There is a resonance form of that fragment where oxygen is sharing electrons to stabilize the positive charge more. So those two forms would technically both exist at 31 mass per charge units, or M-57. Mel, was that a good review? Do you guys have any other questions about how mass spec will show up?
So that blue one that you circled, that's just -73.
Yes.
That's reading the methyl group. Or, like, if you were to draw the...
This produces CH3+. That's what's actually hitting the detector. Good question. Indigo.
When you're separating it, how do you know which side the radical and which side the plus goes to?
Great question. Let's take a look at this here, where I'm going to cleave this bond between the tert-butyl group and the methanol group. Remember, I've got two electrons that make up that covalent bond. And my mass spec instrument is like that BB gun. It's going to pick off one of them. What happens when you lose one electron? You create a hole. You create a positive charge in its wake. So where does the positive charge go and where does the radical go? To both. As evidenced by the fact that we have an M-57 signal, which is when this carbon takes the positive charge, and an M-31 signal, which is when this carbon takes the positive charge. How can it be both? Good. We've got a very small number of molecules coming into the instrument. So there is a chance that this guy takes the positive charge, leaving tert-butyl with a radical, and there is a chance that this guy takes the radical, leaving tert-butyl with the positive charge. And we're finding that it's a much higher chance that this occurs over a chance that this occurs. So if I have 500 million molecules coming in, it looks like about 300 million molecules are cleaving just like this. A majority of the compound makes this fragment. But non-zero, maybe 100,000 molecules cleave like this. And the nice thing is when you've got good sample sizes like that, hundreds of millions of molecules every time you do this test, statistically, you're always going to get that same fragmentation pattern, which is why our mass spec instrument downstairs, it's got a library database of these fragmentation patterns. So as soon as you put in a sample to analyze, it gets this ratio. Oh, I had a mass of 57 this many times with a ratio of a mass of 41 here, a mass of 29 here, a mass of 73 here. And it says every time I get those signals in those ratios, it comes from this compound. Easy way to prove it. Does that make sense? How it can be both? A different number of times? Okay. Kiara and then Aiden.
The question will specify though, like we're looking for M15, and M15 would be, the cation would be the one that's 73, and the negative 15 will be the radical.
Yeah. So this signal at 57 is called the M minus 33.
Yeah.
So there's two ways to name a signal. Name it by its unit, 57 mass per charge, or name it by its loss, M minus 31. So those are the, I think that I'm answering your question right. Those are the two ways you can describe a signal. By its unit or by its loss, the radical loss.
This is kind of question 17, kind of also deals with the molecular ion. I just had a question, more so just for like drawing the molecular ion. So like for D, could you still have could you have the double bond, like if we're looking at citric acid on the top where there's the positive charge on the carbon and then there's the radical on the oxygen. If the double bond still existed from the carbon to the oxygen, could you just put both the positive charge and the radical on the OH group? Or do you have to take out the pi bond?
Okay, so this question says which compound below is a molecular ion for citric acid. There's another version of this question that says which of the compounds below is not a molecular ion of citric acid. What you're looking at are 3 daughter ions. Well, actually, I don't think that's true. I think one of them is isocitric acid. One of them is a daughter ion of isocitric acid, not citric acid. You're looking at daughter ions, though, for 3 of them, and a molecular ion for 1. So I think your question was, could I have drawn a different molecular ion?
Yeah.
Could I have given you that molecular ion? Absolutely.
Okay.
What other molecular ions could I have given you?
The one, what I was thinking is just the radical and the charge on the OH.
Oh, okay.
Is that still fine? Okay. So,
Absolutely.
Okay.
What others? This one? This one? This one? Any of those oxygens? In fact, and this is harder to draw, I could give you this as the molecular ion. Notice how it's a radical cation still? The compound contains both a radical and a positive charge. If it's a radical cation, not always in instrumentation, but yes for this course, if it's a radical cation, it's a molecular ion. I remember one time I gave a bonus problem that said, here is the mass spec for cyclopentane. Draw a possible molecular ion for this structure. There's only one way to draw a molecular ion for a compound that has no lone pairs and no pi bonds. And that's to take out one of any two bonding electrons. See, it's confusing to draw it too, because now this is a one electron covalent bond. 1, 2, 3, 4, 5 atoms. These two are held together by a one electron covalent bond. But that's the only feasible molecular ion that exists. Whereas with these compounds, I can take out a lone pair electron, I can take out a pi electron, or I could take out a sigma electron. Okay. Good on mass spec? Let's talk about acids and bases. I'd like you guys to do a little activity for me. Can you, in your groups, try to define Lewis acid base versus Bronsted-Lowry acid base in a way that you think your classmates would understand? So I've done a bad enough job in class of defining these, and your classmate comes up to you and says, I need help distinguishing these. I can't figure it out. What would you tell them to look for to distinguish Lewis acid base from Bronsted-Lowry acid base? Look back in your notes, use the internet, see if AI can give you a hint, see if it can't.
I think one of them's like all playing or playing, but not clear.
You're on the right track, Will, by the way.
Yeah, so all, yeah, here's the thing. So every Bronsted you're looking at Bronson acids, it's like you're only considering so you can only solve the what happens to that bond?
all squares are rectangles, but not all rectangles are squares. Prove it. Which of these acid-base types is always the other version, while the other version is not always this type of acid-base type? Lewis is always Bronsted-Lowry, but not all Bronsted-Lowry are always Lewis. All Bronsted-Lowry are Lewis, but not all Lewis are Bronsted-Lowry. Does that mean that I can create a Venn diagram that looks like this? Good. And there's actually another circle inside of Bronsted-Lowry that you can make in this Venn diagram, where you can put Arrhenius acids and bases, which have a much more rigorous definition of what acid base is. It's proton donor in water. No. H3O plus generator in water versus OH generator in water. So Arrhenius is like only looking at water. Bronsted-Lowry defines acid as what? Hydrogen ion donor. And base, hydrogen ion acceptor. So if a hydrogen is not being transferred, you are not looking at a Bronsted-Lowry acid base. And to be fair, you don't always see that it's H+, correct? But how often does hydrogen own the electrons in a bond? Very rarely. In fact, we're going to look at a chemical this semester called borane. And borane actually has a 0.1 difference in electronegativity between boron and hydrogen. And that electron negativity lies towards hydrogen. And it's so funny to watch textbooks say, CH is a non-polar bond. Don't think about dipoles. When it has a 0.4 difference in electronegativity. And then they introduce boron, and they're like, think about the dipole. The dipole points towards hydrogen. Yeah, the 0.1 dipole, it's incredible. It's very strong. But it is true. There is a difference that lies towards hydrogen, which means in the cases of reactions with borane, it's actually not Bronsted-Lowry acid, because it's not donating H+, it's actually donating H-. Hydrogen takes the electrons with it. So this is a very rare exception to a time where hydrogen is transferred in a reaction and it's not an acid-base reaction. All right, 9 times out of 10, you look at a hydrogen going from this compound to that compound, that's acid-base reaction. Lewis acid-base. Electrons. Good. All right, moving on. Do you know it's almost always about the electrons? Everything. Unless it's nuclear chemistry, unless you're fusing hydrogen into helium and helium and with hydrogen into lithium and lithium with lithium into carbon, it's almost always about the electrons. That's why we talk so much about electron orbitals. That's why we talk about bonds. That's why we talk about electron arrows, because electrons determine all of your chemistry. What do I need to add here? Pair. Okay. I still don't think this is a good enough definition, guys. If you see an electron pair, you've got a Lewis acid base. Give me more. Okay.
I thought we were assuming.
Well, you know what happens when you assume. Here's my challenge about this term, electron pair donor and electron pair acceptor. You'll see chemical reactions where there's a lot going on with electrons, right? Like one compound is taking its pair of electrons and donating it to a compound that then has a bond breaking. So is the bond breaking an electron pair acceptor of its own? Is there multiple Lewis acid base things going on? Not necessarily, but I feel like there is kind of a poor definition in there, or a challenging definition to describe. How else can we name Lewis acids and Lewis bases? Good. So the Lewis acid, which is the electron pair acceptor, nucleophile or electrophile? Does it love nuclei and it wants to bond with them, or does it love electrons and it'll take it from anywhere? Loves electrons. So we call these electrophiles. And by the way, is it a Lewis acid or a Lewis base? I'm sorry, is it a Bronsted acid or a Bronsted base? That is a Lewis acid.
No, it's the acid.
Oh.
I'm pretty sure the acid is the acid.
If an acid gives up H+, that means it's actually taking electrons for itself. And if a base is donating H+, the base has to put electrons in to take H+. So a Bronsted-Lowry base is the Lewis
Oh,
base.
so they're swapping like a lone pair for a hydrogen.
Yeah.
Okay.
So Bronsted-Lowry acids are Lewis acids. Bronsted-Lowry bases are Lewis bases. And then we've got the Lewis base, electron pair donor. And we call this the nucleophile. You know, I don't want to do too much with last year's exam or the summer exam, because I know that you guys, some of you still want to use it to review. So I think I'm going to go back to an even older exam, and I'm going to show a problem from it so that you guys can see another example. I think there was one year my students really hated me for it, so I think that would be the right one to go to. Oh, right. Yeah, I used to do multiple exams too, like 3 midterms before the final. I didn't like that stuff. That was too hard. Okay, I've got the wrong one. Okay, no, I'm sorry. Can't find one. I'm just going to draw an example up here. We'll start with this cyclohexene. And we'll react it with HBr. Anybody know the name of HBr? Don't be shy. Hydrogen bromide would be okay if you're calling it from a covalent molecule kind of perspective. Hydrogen bromide. Hydrobromic acid is its acid name. So hydrobromic acid, what role do you think it plays in this reaction? I'm not joking though. Like, that's how easy organic chemistry is. Think about the name, that's the role it probably plays. So if this is an acid, then this is a base. And we're looking at Lewis acid bases, but in this case, we're also looking at Bronsted-Lowry acid bases because there's a hydrogen ion to be donated. So HBr is the hydrogen ion acceptor. It's also the lone pair, hydrogen ion donor. It's also the lone pair acceptor. If it's going to donate H+, do you agree that the HBr bond needs to break? Who does it break to? Who owns those electrons? How do you decide that bromine owns the electrons? Electronegativity is always a good bet. So bromine owns the electrons, it takes them back. What do bases do? They accept hydrogen ions. How do they do that? They donate their lone pairs. They donate their pairs of electrons. I said lone pair, but it doesn't have to be a lone pair. This is a pi electron pair. And the alkene is actually going to donate its pi electrons as the pair of electrons. Bromine goes from 3 lone pairs to 4, gives it a negative charge. One of those carbons, it's not up to you to have to decide which right now. One of those carbons uses the electrons and bonds to the hydrogen. The other carbon loses the electrons and bonds to the hydrogen. So, which of these compounds is the nucleophile? I've got 4 structures. Let's label them A, B, C, and D. Which of these compounds is the nucleophile? Raise of hands. Aiden. A is our nucleophile. It's the electron pair donor. Which of these compounds is the conjugate acid? Raise of hands. Will?
It's C.
C is our conjugate acid. Feels odd, yeah, but C actually has a positive charge now, and it could give away a hydrogen, and it would go back to being an alkene. Okay. Which of these compounds is the Bronsted-Lowry acid? The electrophile? Raise your hands. Kiara. B is our Bronsted-Lowry acid, aka the electrophile. Good. I feel like I kind of did all of them. The only thing left is what's the conjugate base? D is our conjugate base. It's not a very good base, by the way. It's a pretty bad base, but it is a conjugate base. How do we feel on Lewis acids and stuff? Do we want to look at more of that?
I know that we're trying to stay away from the midterm that was posted, but
No, it's okay. I don't want to lean into it too often. But if you've got a question on it, we can look at it.
the part that really confused me is where did during the reaction in 24, where did the CH3, why isn't that still CH2? Where
Okay.
did the extra hydrogen?
Where did the extra hydrogen come from? Anybody want to answer this? I realize now this is like so similar to the problem we just did.
I thought that was kind of
Yeah. not entirely.
well, my thought is that it's coming from the acid when it breaks from hydrogen and bromine.
Yeah.
Because hydrogen has to go somewhere.
Gotta go somewhere.
So it just
What you're doing is spotting the difference, right? This goes from CH2 to CH3. I'm increasing in hydrogen. This goes from HBr to Br minus. I'm decreasing in hydrogen. And this goes from how many hydrogens? One more time. 0 hydrogens. Can you be confident on that? There's 4 bonds already to that carbon, so there can't be any hydrogens. To how many hydrogens? Still 0, because it's a positive charge now with only 3 bonds. So there are no hydrogens bonded there. So this carbon is not changing. But this carbon is increasing by 1 hydrogen. So we're looking at the exact same thing. The pi electrons are leaving. That's a bond that breaks. And it's increasing in hydrogen. So it's breaking its pi bond and using it to bond with the hydrogen. Should I show it? Because you guys have the answer key.
Do you have to draw another arrow showing the hydrogen from the bromine going to?
We don't show arrows. This is a great question. We don't show arrows for atoms moving.
Right.
We show arrows for electrons moving. Because the atoms aren't doing anything. It's the electrons that are changing. You guys remember when I brought in those magnets? I know that we're drawing these as stationary, flat, two-dimensional structures, but they're actually quite wobbly, as we saw in Unit 2 when everything had these different conformations and their energy, or they're moving all around all the time. And they're moving through space all the time. So once this molecule rams into this compound, then this reaction takes place. So I don't have to show any of the hydrogens moving or any of the atoms moving, just the electrons. I will say this. How would you know that of these two carbons sharing these 2 pi electrons, this is the carbon that's using the hydrogen? How do you know? Because it's drawn for you in the product. That's it. That's the only way you can know which of those carbons is using them. You see it once it's drawn in the other structure. In the second half of the semester, I'm actually going to teach you how to figure out which of those carbons is more likely to use them, because it's not random. It's not random that this carbon uses them and this carbon loses them. It's very predictable, but you don't have to predict. It's just shown for you. All you need to show are bonds that form and bonds that break. Here's a bond that breaks, here's a bond that breaks, and here's a bond that forms. Here's the deal. I had a lot of students on this exam that actually drew this. And I did take some points off for it. Because this arrow is starting from an atom. It's not starting from an electron source. It can't start from an atom. It has to start from an electron source. And I get that they're trying to show these electrons go to this carbon, and then this carbon uses them to bond to the hydrogen. Well, you don't need to say that the electrons go to that carbon then. In fact, maybe this is a good way of demonstrating it. Have the arrow run through that carbon atom, so you can, in a way, say, this is the carbon that's going to go grab the hydrogen. This is the carbon using the electrons.
So what can you draw arrows on then? Lone pairs and bonds?
That's it.
Okay.
Arrows start from lone pairs and bonds. Arrows can be drawn to atoms and bonds. If it's drawn to a bond, that means it's going to make a double bond. If it's drawn to a double bond, it makes a triple bond. All right, here's what I gave to that one class that didn't like me much by the end of it. I asked them to draw me arrows for this, and that was a step too far. There's a lot that has to go into it. First of all, recognize bonds that break. Carbon-carbon double bond breaks, bromine-bromine bond breaks. That means I need to have arrows that start from there. And then look at all the bonds that form. There's actually 2 carbon-bromine bonds that form. So I need to have 2 arrows that show the formation of a carbon-bromine bond. One way that I can do this is to have the carbon-carbon double bond indicate the formation of a carbon-bromine bond. That only shows the formation of one of those bonds, though. When the bromine-bromine bond breaks, I know which way it breaks. I can't take these electrons and use it to come back at the carbon, because this bromine here needs to become bromide. It needs to get a pair of electrons. So then how do I show this other bromine-carbon bond forming? I have to recognize that this bromine goes from 3 lone pairs to just 2. How do you know there are 2 lone pairs on that bromine? Your ABCs, that table of common bonding patterns. There's very few things going on with halogens. This is one of them. 2 bonds, 2 lone pairs, 3 lone pairs. That means one of those lone pairs is actually being used to form a bond as well. So I just thought, they'll get it. And then, of course, in the second half of the semester, we go through this reaction. We go through this mechanism. It's one that you're expected to show me on the final, or one of a few that you'll be expected to show me on the final. And they came back and they said, you gave us that question way too early. I didn't. I gave them that question expecting them to use the idea of what bonds break, what bonds form, what way do electron arrows move. But I do recognize it was too many arrows in not enough steps. So I have scaled it back from that part of the mechanism. I think on one exam, I actually gave this, and I asked my students to show me arrows for this step of the mechanism. Raise of hands, what bonds break? No? Cyclohexane. Oh, yeah. One of these carbon-bromine bond breaks. What bonds form? Yeah, the other bromine bonds to the same carbon that actually broke its bond to the other Br. So if I have to show one of these 2 bonds breaking, I'm going to start my arrow at that bond and point it towards carbon or towards bromine? Towards bromine. It doesn't matter which one I choose because with the information I have right now, they're identical. So I'll show this bond breaking. And that carbon is now losing electrons, so of course it wants to accept electrons from something. So it would accept electrons from this bromine. That's how I can get 2 separate bromines. Now that's more reasonable, would you agree? All right, let's tie it back. Here's A, here's B, here's C. Which of these is the electrophile? A is the electrophile. And the nucleophile? B. Bromide uses a pair of electrons to share. It donates it to A. Again, this is why it feels weird to say that A is just an electrophile, because there's some weird bond stuff going on here as well. Is that an electron pair acceptor, electron pair donor? Seems weird. Nucleophile seems pretty easy. This is just donating electrons. So that means this must be the electrophile. Which of these is the Bronsted-Lowry acid? Elliot brings up a good point. No hydrogens involved in this reaction. Lots of hydrogens, yeah. But no hydrogens involved in the bond forming or bond breaking. So no Lewis acid, no Lewis base, no Bronsted-Lowry acid, no Bronsted-Lowry base. just Lewis acid, Lewis base. This chemical reaction happens up here, whereas this chemical reaction happens in here. All right, I know we're running out of time. I also forgot to say this. I forget to say this all the time. I probably won't take a break today to give you guys the most time for your studying. But if you need to move around, go to the bathroom, get a drink, feel free to do that. I know that feels kind of rude. It's like, go do what you need to do. I'm going to keep doing this. But that's to give you guys the most time. All right, let's talk about R&S priorities, because I think we can knock that out pretty quick, and then we can spend a little bit more time on IUPAC nomenclature. Sound good? And Indigo, I believe this was your question, is that right?
Yeah.
You wanted help, especially in determining priority.
Yeah, like how different functions are set of priorities. Give us that list. I just want to see like a couple examples.
Oh, that list of priorities is actually not about R&S priority.
Otherwise,
It's about IUPAC nomenclature priority.
can you go over the priorities for us?
Absolutely. This is isocitric acid. You can abbreviate this structure if you want to by turning all of those carboxylic acid groups into CO2H. So if you don't want to draw all of them out, you can just draw CO2H, shortens it a bit. I'm going to make 2 chiral centers. I gotta say, on my exams, I love my first 2 pages. In all reality, if I had to ask you guys a certain number of questions and get a certain number of concepts across from you from all of organic chemistry, it would be these. These first 2 pages, truly what I want you to take away from organic chemistry. The ability to look at a structure and provide endless amounts of information about it. How many lone pairs are there? What types of bonds are there? What is the hybridization? What is the molecular geometry? What is the acidity? Tell me about carbon substitutions. Tell me about intermolecular forces. Tell me about polar bonds. Tell me about chirality. Tell me about structural isomerism, stereoisomerism. Tell me about spectroscopy. It's just like, it's everything, and I know that can feel pretty heavy, but I think for the foreseeable future, my exams will always have these first 2 pages with questions on these lines. Tell me everything you can about this structure or these 2 structures. These 2, I think, were pretty cool. You guys know where these 2 molecules show up in your body? Yeah, it's pretty well known as the citric acid cycle, also called the Krebs cycle. Terrible. Name it after a guy when you can name it after the compound in it. So any of you that go on to take biochemistry, you'll get to know these compounds really well. And I bet you'll be probably the few people in your class that say, well, I can look at it and tell you all of the lone pairs that are not shown. Because nobody else is being asked a question like that. Whereas I think that's one of the most valuable things. It's something we're assuming, right? When we talked about bond line structure, we said we have to assume lone pairs. Everybody else forgets about it. They forget how to count lone pairs. This is something I need to see that you can do for my sake. Okay, so I've got isocitric acid here, and I've got 2 chiral centers. We're going to figure out their absolute configurations. Step number 1 in determining chirality is to assign priority 1 to 4. And what do we use to assign first priority? Highest atomic mass. Despite the fact that some places on the internet will tell you you can take the mass of a group, don't ever listen to them. You should always look at the first point of difference. And I really want you guys to convince yourselves when you're at a point of difference. Let's take this central chiral carbon and we'll go from here. Is it easy to assign first priority just by the atoms attached? Carbon, carbon, carbon. No. But that means it is easy to assign fourth priority. Hydrogen, that's assumed, going backwards. All right, so I gotta go beyond the first carbon that I see. Here I have carbon, then oxygen. Here I have carbon, then oxygen. Okay. Here I have carbon, then carbon. So do I know priority number 1 yet? But I know number 3. So one of the carbon to oxygen groups is going to be my first priority, but I have 2 of them. So this is priority number 3 because it's a carbon. One of these groups is going to be my higher priority. Okay, what's the next highest priority atom off of this group? Also oxygen. What's the next highest priority atom off of this group? Just a carbon. I already considered this oxygen. It wasn't my next highest priority, or it tied anyways. So then the only other thing that could have a fighting chance is this next carbon. And it's not going to win out against this. In fact, those double bonds to oxygen, they count as 2 separate bonds to oxygen. So when you're looking for the first point of difference, you can count double bonds twice. Here's a way that some people would like to map this. Here's my central atom. Going to the right, I had this carbon, oxygen, carbon. Going up, I had this carbon. And then, in fact, it's like having 3 different bonds to oxygen, because I've got the double bond and the single bond. And going to the left, carbon to carbon. So this group lost because it had a fewer number of oxygens bonded to it. All right, here's priority number 1, priority number 2. Honestly, the rules here, I think you can combine and separate the rules as you need to make it make sense. I think in class we said rule number 2 was place priority 4 backwards. Done? I don't think I said anything. I think I drew it back. I wouldn't say down. I would have said back. Down is dashed. When we talk about chair conformations, we say a dashed is a down group. With it in the back, step number 3 is determine rotation. And which priority groups do we pay attention to when we determine rotation? Why don't we pay attention to 4? Maybe. I would say we actually already are paying attention to 4. We paid attention to make sure it's in the back. And if it's in the back, Then rotation from 1 to 2 to 3 gives me everything I need to know. I'm already considering priority number 4, just based on its positioning. So 1 to 2 to 3, clockwise, this has what configuration? R. All right, now I realize I actually wanted to do the other chiral center dashed instead of wedged. From my chiral carbon, what is the first priority group? Do you want to give this one to me? What's the highest priority? From my chiral carbon, the oxygen of the alcohol. Do you want to give me priority number 2? Good. Carbon to carbon ties. Oxygen to carbon. Either direction I go, I'm going to lose oxygen to carbon. So here's priority number 2, number 3, and this time priority number 4, hydrogen, is not back, which means I'm breaking rule number 2. So we had a tip about this, right? What did we say? Yeah, determine the rotation and assign opposite of a parent. Because it's like we're trying to tell the direction of rotation of a clock from the position of the numbers. So it looks like 1 to 2 to 3 is going counterclockwise, but I'm looking at it wrong. And if I put myself back in there and flip myself around, is it going counterclockwise? No, it's going clockwise. Good review? You're welcome. Any other questions? Let's look at nomenclature. Remember that we can break down a molecule's name into this, like these 4 parts. And remind me, for most molecules, which of these 4 parts makes up most of its name? The prefix. Because those prefixes are where we put all the substituents. And a lot of compounds have a ton of substituents. Honestly, you have just one substituent, you've got like equal parts prefix to the rest of it. And then you get 2 or 8 different substituents, you got this huge molecule, and just a tiny little bit of it is describing the parent chain. So this will come back to what you talked about, Indigo, as a good review of the priority of the functional groups. Although you're not going to have to prioritize the functional groups until the second half of the semester. But our first priority for the lowest locant set, remember that that's what we're looking for, is lowest locant set. Our first priority is if we have an alcohol. We want the alcohol suffix OL to have the lowest locant set. And this is actually just for OCHEM 1. When you get into OCHEM 2 and you're introduced to more functional groups, it expands. The second highest priority functional group is both ene and ine. I didn't really mean to not fully put ene. Ene and ine are tied. You want either one of them to have the lowest locant set. But if you're numbering a compound and you have the choice of either of them having the lowest locant set, then, as always, alphabetical order wins. Whichever comes first alphabetically. What comes first between een and ein? E comes before Y. That's it, actually, in terms of suffixes. Because if you don't have anything else, if there is no other functional group, then you give it the suffix ein. Right? Because with alkyl halides, it always shows up as in the prefix. The root, we're looking for the longest parent chain. And there's some weird things here, things that I don't usually give to you on these exams, but the longest parent chain with the highest priority functional group and with the most substituents. You remember you had that active problem that was like, number the chain this way, you get heptane, number it this way, you get heptane. But numbered one way, you got 2 substituents, and numbered the other, you got 3 substituents. You're going to choose the longest parent chain that contains the highest priority functional group, contains the alcohol, contains the alkene, contains the alkyne, and also maximizes substituents. It's rare that you see me give you a problem that doesn't have maximum substituents, or 2 different routes that have different amounts of substituents. All right, then the prefix. What we aim for in the prefix is having the lowest locant set. That's if we don't already have a suffix functional group that has claimed priority of the lowest locant set. If you've got an alcohol, it doesn't matter what possible locant sets are out there. You number in such a way that the alcohol gets its lowest locant. But if you've got 8 different halogen positions, you're going to number in such a way that they all cumulatively have the lowest locant set. You've got halogens and alkyl groups, methyl, isopropyl, tert-butyl, fluoro, chloro, bromo. All combined, you're aiming for the lowest locant set. I want to remind you guys, I think I fixed an error this semester in the pre-reading quiz. Halogens have no priority over alkyl groups. Halogens are equal to alkyl groups. All you're looking for is the lowest locant set. Then if there's a tie between 2 locant sets, then you award it alphabetically. And there's a good chance the halogen wins alphabetically because you've got chlorine and bromine. Those show up very early in the alphabet. But you've also got things like sec-butyl and tert-butyl. Those also show up early in the alphabet. So the only time a halogen gets the lowest priority intentionally is if it's the first alphabetically and you've got 2 locant sets to fight between. And then the name is alphabetical, always. Yeah, LMNOP-QRSTU. So bromine comes before butyl because R comes before U. Isn't that crazy? You got to go through the whole alphabet to figure it out. And who decided on the order of the alphabet? We should have a meeting about that. You know, actually, a lot of languages across the world, their alphabet starts with those same two letters. Their A sound and their B sound. Alphabet is literally just the Greek A, B, C. The Arabic language, Alif Ba. The Hebrew language, I think it's also Aleph Bet. I don't know. Give me another. It probably is the same. Maybe not all languages, but anyways, I digress. I don't think IUPAC actually won that battle. Okay, Will, I know this was your question. So have we touched on things here that you wanted to review, or can we dive in a different direction that's going to help you?
That's pretty good.
Yeah?
I feel like, yeah. I just wanted to go over like what all those different things.
You guys know we spent like a class period on nomenclature, maybe more. And we've just summed it up into this little diagram. That's what reviewing should feel like. Reviewing should feel like it took me an hour, 2 hours, 3 hours to learn this. I practiced it on active for how many hours, but I can review it in this cute little graphic. And something like that goes right on your note card with maybe an example. An example of a molecule like we did in class, or one that you saw on the unit test, or one that you had on active. Examples on your cheat sheet are super useful because it's not just words that you have to read through and decipher, but it's a way to say, if I see something like this, I know how to respond. Guaranteed, in the same way that I love to have these front 2 pages of multiple choice questions, I love these draw a compound, because that tells me you know how to draw IUPAC nomenclature, and identify why it's wrong, rename it. But I have to tell you guys, semester after semester, there is something wrong with this name. So please, for the love of God, do not put nothing, you screwed up, there's nothing wrong with this. There is something wrong with it. I choose that intentionally. Or I get these answers sometimes that are like, oh, you put one of the groups on the wrong carbon. Nope, that's not what was wrong. So show me that you know how to draw a compound based on its name. And then once you've drawn it, honestly, regardless of what you've drawn, name what you've drawn. I never, ever want you guys to look back up at this name. I don't. Once you've drawn it and you feel confident that you got it drawn based on that name, don't look back at that name. It's just going to throw you off. Because you're going to think like, well, how can I keep pentane in there? How can I keep 2,3-dibromo? How can I keep the pieces I was given? No, don't. Start over. Use these rules. Identify the longest parent chain. Give it a root. Identify the suffix. Identify the substituents. Identify the locant set. Make sure you have the lowest locant set. Start over completely. Don't look at the name that was there. Then once you've got a new name, you can compare them and figure out what mistake they made. All right. I know we're pretty much wrapping up on time. Any last questions that we can look at together?
So just to confirm, so the locant set, so like is like a way you can determine the lowest locant set if you're like debating between a couple of images, if you just like take all of the numbers and sum them up, like whatever the lowest set is that what you're looking for?
No. No. Sorry, earlier when I was talking about R and S priority groups, I said don't add the mass of the groups. Some places will tell you to do that. Actually, I think I was wrong. Places won't tell you to do that. This is where people will tell you to do that. They'll say add up the locate set and get a sum and just compare those numbers. No, you can't. I think we did an example in class where one locant set had the lowest locant at the first point of difference, but a larger total sum. And the other one had not the lowest locant set at the first point of difference, but a lower total sum. The total sum is not the answer. It is the lowest locant set. Same thing as this. Lowest locant set at the first point of difference. So you're looking at 1, 2, 5, 7 versus 1, This is probably a real thing, so I gotta be careful about this. I don't know. Let's say 1, 3, 6, 7. I think actually I might have that right. Which of these locant sets wins? Why? Good. 2 is lower than 3. That first locant, not a point of difference.
Okay, so you're looking for a minimization, not a sum. Okay.
Not a sum. Please never sum your locant sets. That's not the goal.
Got it.
List them and find the lowest locant set at the first point of difference.
I just wanted to clarify that because I think that's been most confusing sometimes.
It's a good question. Yeah. Okay, so now that Canvas is open, what I'm going to do actually right now is publish. I'm going to publish a review. Sorry. Unit test questions. All unit test questions will be accessible to you. That means that tonight and tomorrow and Wednesday morning, you can go through these unit test questions. They are all of the questions that you had on your unit test and all of the questions you didn't have on your unit tests. All of the questions from all of the banks. That means I think there's something like over 100 questions in here. So, no, 99. Don't go through all of them if you don't need to. If you feel confident on a subject, go past it. Go find the questions that you think you need help with. This should help you. All of the short answers are in there as well. And I don't have like a solution to all of the short answer problems. But at least you'll get that attempt at all of those different short answer problems. Feel free to send me a message if you want me to check over something for you. All right? You've got that and the practice midterm and all of our learning objective sheets that are at the top of the unit modules. So you can go through that and say, yes, I understand that concept. I know what this is asking me to do. I feel confident on that learning objective. As a reminder, this is what I'm talking about, these documents. Can you go through and make sure that you understand each of these learning objectives for the different units? Okay. Have a good night, guys. See you Wednesday in here, 5 o'clock. Actually, we'll do about like 10 minutes of Q&A and settling in. I know some people come in a little bit late. So we're going to start at like 5:10, 5:15. And we'll run for 90 minutes until 6:45. Okay? Have a good night.
If I have accommodated testing, I just don't come.
Did you get my email?
Maybe.